Uh, okay. Okay. So let me whatever we have talked about till now was doing some high resolution sensing using different type of systems for different applications. When I say different applications, you may realize that these are all very advanced applications where resolution is really a challenge, and then we are trying to address them by one system or the other. Then another way people are trying to beat the some of those I should say beat some of the numbers is using some quantum systems. And one such quantum systems people use is making a single photon. And therefore, the 20th century was, all of us know that there was information science, and then we do have quantum science there, but integration of both information science and quantum science is what will going to give you quantum information science for this 21st century. And this is what we'll see quickly that how it can be utilized. Now, all of us know that one of a very strange feature of a quantum mechanics is that all particle can behave like a wave, and this is what we know that all particle in this universe can behave like a wave, and then therefore it become much more interesting to just see that how uh, how can these particle which behaves like a wave can be utilized for developing such quantum systems. If you take a 1 milliwatt laser source operating at, let's say, this numbers, you get around 10 raised to the power 15 number of photons. We are talking about one photon, single photon. Then it is really bothersome that from 1 milliwatt laser source itself is very low power, and from there getting down to this number is extremely difficult. But then there are techniques to do this. One is called as a multi-photon. You create multi-photon and then you attenuate them using some attenuator, and you get single photon. So you can think like making a very dull light source, and then you can use them to get single photon. By attenuating the light itself, you make single photon. This is a very standard technique, which are also now commercially available in the market, what are called as an entangled photon source using nonlinear process. So you basically have a pump. You pump a nonlinear material or crystal, which can be LiBio or lithium niobate people are using, and then you create two photons. Now these photons are entangled, but these are single photons. And then people do the study of this single photon for different applications. Another way to create single photon is using a material approach, that you take some type of a material, which are basically quantum dots. You pump the energy, you pump these electrons in the excited state. It comes down to a lower energy state. And since we are talking about some quantum dot type of a system, we know that this energy, we are considering this energy level to be discrete. And then, going by the concept of particle in one-dimensional box in quantum mechanics, you can see that you get some photon, single photon. We can use this as a thing. Now, this single photon are required, if on a bigger picture, if I see, can be required for, we'll be talking about this process, not about this process. So this single photon on a bigger picture can be required for quantum internet. Currently, what we are using is a classical internet. You send 0 and 1. But the idea is these are bit, but can we have a qubit or quantum bit, which are superposition of 0 and 1? And this was given by J.F. Campbell. Unfortunately, he passed away last year. And he gave this concept. There is a paper in Kimball in Nature, which is came in 2008. So he said that if you have a two node, don't worry about what node is, I will discuss about it. If you have a two node A and B, and if you have some state existing here psi, and you want some another, which is a state, this is a state A, this is a state B at some time t. You get some gamma or some photon, and you want to measure them there. So it can travel through this open air medium. So these are some sort of a cavity which is open cavity. Similarly, in optical fiber case, you can have a closed cavity on which can go via fiber. So what is quantum internet? It is a sharing of information at atomic level through quantum channel. So what are quantum channels? In this case, this is your quantum channel. Now, what you are seeing here is very far apart. Ideally, it should be of order of nanometer or less than that. Similarly, what is a quantum channel? Some type of a processed optical fiber will act as a quantum channel here. So sharing of information at atomic level through quantum channel. So you have a quantum channel here. And atomic levels means you require some sort of a atom. And this is what is, this is what is, uh, this is what I will talk about. So your quantum interface or channel can be either optical microcavity, it can be optical nanowire, like in this particular case, it can be some plasmonic nanorod, it can be metal. Similarly, the one which is required at atomic level, which are called as a quantum node here you can see these nodes. These are basically nothing but these are one of these items, like either trapped ions or neutral atoms or solid state qubits generated from quantum dot or NV centers or 2D materials or superconducting qubits. So you have these materials here, and then you have a channel. You create the single photon, you couple them either through air, which if these are separated, if these quantum channels are very small or very narrow, and either you can put them through some type of optical nanowire. So these are two important components required for quantum internet, which relies on qubit, which can be generated using single photon. So this is what I have just tried to summarize for you in one slide that how does it look like. So if you can somehow think that if you can create a single photon system, how to create a single photon system? I have told you that you take a quantum dots, do something correct fabrication of quantum dots, you can create single photon. Now this single photon can be utilized for quantum photonics, it can be utilized for quantum plasmonics. How? For example, these quantum emitters or quantum dots, if you have a nanowire, optical nanowire, if you have optical nanowire, and if you make a grating inside these optical nanowire, then these quantum emitters or quantum dots, if it radiates, it can get, if it can get coupled to these what are called as cavity. This is your cavity because these are grating, you know that these will act as a mirror. So it will get coupled here and it can be trapped inside this. Or you can make some sort of another slot inside these optical nanowire and you can put your quantum emitters here. So if you see carefully, I will just try to play this video. If you see carefully in this particular video that if you have a quantum emitter which is placed here, you see this quantum emitter will get coupled to these different cavities which are placed here and it get propagate here. And what are these? These quantum emitters, you know that these are single energy, two energy level systems. So these are basically giving you single photon. So one can create these single photon and it can go into both direction. Therefore, these act as a bidirectional. Similarly, you can, if you have to make a unidirectional cavity, you have to play around with this structure further. That means you have to, if you see here, these are two, I have shown you two black dots. These are basically some sort of a grating structure. But if I make these grating structure non-symmetrical or unsymmetrical, that means on one side I have less number of grating, another side more number of grating. And if I put my quantum dot inside some slot, then you can make out, you can see that this is computationally generated. You can see that all the single photon is coming from this side. 90% of the single photon comes from this side. Unlike if you just do not have this BG. What is BG? This is Bragg cavity. These are what is Bragg cavity. If you do not have a Bragg cavity, then only 57% comes from one side. So one can make, create this single photon, and depending upon your requirement, either you can get from both the side or from one side. You can put this single photon between gold nanorods. These are under the, these will going to create some hotspot due to the, oscillations of coherent electron. So these create hotspot under this field, these quantum emitters or quantum dot decays, and it gives you polarized photon. So plasmonic cavity give you a very high value of polarized photon, or degree of polarization is very high. Then you can make use of both. I mean, these are example of hybrid photonic plasmonic. So basically, plasmonics are utilized for creating a polarized single photon. So this I thought that maybe just to tell you what is latest going on in research. So with this, I think let me summarize. Typically, what we are talking about, we have talked about some optical interfaces which are, you know, it depends upon wavelength, but typical resolution is typically nanometer and sub-nanometer. Limitations, of course, vibration does it do play a bad game, but it can be utilized for a lot of applications. There are spectroscopic techniques which can again go to zero point 0.1 nanometer. A spectral resolution can be this, and these are required for gas sensing and stuff. I have talked about STM and TM. Of course, it gives you in this range, but one can go beyond that, as you can see from here, that it can go beyond these numbers using some of these optical interferometers. Similarly, for AFM, these are all electronic systems, go to sub-nanometer height. Quantum sensors, I have not discussed much about quantum sensors due to paucity of time, but NV centers is something which uh, is some type of a defect in a diamond, and these defects in diamond are required to defects is generally we don't require. In the last class I mentioned to you that in defects in diamonds are something which is more exciting for engineers and physicists, because you can excite these defects carefully and can apply some external field to detect magnetic field. So please note the magnetometry that I have discussed with you with interferometry typically give you millitesla, right? But with NV centers type of quantum systems, you can go to femtotesla magnetic field or picotesla magnetic field. So this is what is the beauty of pushing the resolution limit with the quantum sensors. We talked a lot about fiber optic sensors. Of course, there are plasmonic sensors. I have talked with you about near field, how it can be utilized for near field and far field. And of course, all these can be integrated with AI nowadays. Many things are getting integrated for further boost the resolution limit. So I think with this, I will thank you very much for your kind attention, and I will be happy to take few questions before I move to the next part of
my talk. Thank you, sir. So there are few queries.
Yeah.
Can I read or you can also see the chat box?
Okay. It's opening. Okay, so I can see there are quite a bit of questions here. No, it is good afternoon. Have all started or not? Good afternoon, sir. There are many technical issues to join, and we could not join first 3 days session. I think this is good morning. Good morning. Good morning. Can we use interferometer for earthquake detection? Yes, we can use Rajesh Chaurasia ji. We can use interferometer for earthquake detection, and people are using that system only. People are basically detecting the earthquake. It is possible. What challenges exist in implementing high resolution sensing in photovoltaic fabrication? High resolution sensing in photovoltaic. So any material parameter, photovoltaic, whenever you are talking about, you are basically characterizing materials. And as I talked with you that, and if you do the characterization of materials, the surface morphology, the uniformity of the surface roughness, the thickness of the film, all these will going to play a very important role, for which you require a very high resolution systems. And I talked with you about these ellipsometry, laser-based ellipsometry, or for this one for other case, the nano displacement sensor, which I talked with you about, can be utilized for, can be utilized uh, for while developing the photovoltaic systems. Is it least count is an example of resolution, sir? No, it is not exactly example of a resolution. Least count is the smallest measurement that can be done when we say, but resolution is slightly different than the least count. But when I was trying to explain you, I try to put in more simpler language so that you can appreciate it better. How effect of EFSR value for the position of refracting surfaces? How effect of FSR value for the position of refracting surfaces? Sarfraz Khan Saab, I did not get you exactly. If you can rewrite or reframe your questions, I can get back. Single photon one, single photon, sir, biomedical. Is there any bandwidth constant for the Mach-Zehnder interferometer? Uh, Arindam Mukherjee, what do you mean by is there a bandwidth constant for Mach-Zehnder? Any device, optical device, if you are using, it will always come with a bandwidth. The bandwidth is largely getting dictated by the source that what you are using. If there is some circulator that you are using, if you are talking about a fiber optic based Mach-Zehnder, of course, uh, you don't use a circulator there, but then the interrogator systems that what you are using decides the bandwidth. It is not that you can use the uh, interferometer for any value of bandwidth. It get decided by the line width as well as the spectral width of the source. Can you brief about quantum sensing application or blood analyzing applications? Biomedical, I will be talking about biomedical applications. How can plasmonic sensor comes under quantum realm? Lakshmi, the quantum is plasmonic sensors. Please note, plasmonic systems are one which you try to interrogate at dimensions which are closer to tens of nanometer. So you can utilize the plasmonic field or the electric field which are created by the plasmon, and under that, in the presence of those electric field, the quantum emitters or the quantum materials that what you choose can further get enhanced. Means the 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 emission that will be given or the photon that will be released by the quantum emitters under the influence of a plasmonic system will get enhanced. Also, since many of these plasmonic systems are polarization dependent, you can make a polarized single photon using such type of integrating plasmonics with the single photon source. Can you suggest a simulation software? You can use finite element method or finite difference time domain for sensing application. I think this is what I can see all the different questions. Except Sarfraj Khan Sahab, how effect of FSR value for the position of refracting surface. So as long as from any surface, if I can understand your questions correctly, if you are able to create an interference pattern from any refracting surface, so once you have a FSR, if you want to create FSR from different surface which are refracting, the whole idea is you need to create a interference pattern and it should fulfill the condition for interference pattern. Once you have a condition for interference pattern being fulfilled, then you will able to create. But how to control the FSR is something you have to come up with some system where you can control FSR either through optimizing the cavity length or through changing the refractive index. I mean, there are few parameters or operating wavelength. There are few parameters on which FSR depends. So you have to tune one of those parameter in order to get that. I hope I am clear. If there is any more questions, you can you can share it here. In the meantime, I will try to go to the next part of the talk and we'll take those questions again. Can you see my slide?
Yes, sir, slide 7.
Okay. So if you see the second session, I mean, which of course is getting delayed, I will try to catch up as far as possible. Is the requirement of a high resolution sensing in biology, medicine, aerospace, and mobility. Now, this only reminds me that nothing is more or less left under this umbrella of developing a high resolution sensing. So I will try to just cover few of the aspects which I think should make the things more clear. So what will be the outline of this talk? Under biology and medicine, we'll talk about some selective biochemical sensing and some wearable healthcare systems for healthcare. Why wearable healthcare systems? We'll talk about this. Under aerospace, I will try to tell you about how we can detect microcrack. Under mobility, I will try to tell you about how can we do about smart traffic monitoring through. And if time permits, I will try to talk about how magnetometry can be utilized using NB sensors. Let me hurriedly go to these biochemical detection, uh, or I should say that in this particular case, we are talking about water pollutants. And this is one of our water pollutants. You can look into these are one of the detrimental water pollutants which people are trying to detect. Now, as I told you in the mention that one of a very advanced or sophisticated system, what we have is an interferometric based system. And this is exactly what we are trying to use here. So we are also trying to integrate with some very sensitive technique like microfibers, or I should say some processed optical fiber, and then using all of you will appreciate that there's a term called as a lock and key arrangement. That means for a given lock, you need to make a key, then only lock can be opened. Something very similar to this. So what we do is we take some bare microfibers. You can see that these are microfibers, and then using some nano imprinted polymer, which are some sort of a nanoparticles, we try to functionalize these microfibers. So you see that we have functionalized these using some type of nano imprinted nanoparticles. And once you functionalize them using these, then you can put some sort of a very typical. You see that on this, you will realize that there are some star shape yellow spots that are there. So corresponding to these star shape yellow spots, you create. So these are basically the binding sites. So you try to make some molecule which will fit to these binding star shape binding sites itself. So if these fits properly, then what do you expect that the around these microfibers, the local refractive index will going to get changed. So once the local refractive index change, the different modes, optical modes or the microfiber modes, what it will going to interact with, the these modified functionalized microfiber probes will going to get changed, and then we try to detect those changes. So what it then boils down to? It boils down to the fact that you can see that these are different steps, and these are some interference pattern which I am trying to show you here. These are some different interference pattern. So the whole idea is you functionalize the microfibers, and then based on the lock and key arrangement, you for example, if you want to detect a parathion methyl, so you have to make these you have to imprint the template corresponding to parathion methyl on your these bare fibers. One can create them in the lab. And then whenever the parathine, so once you have this parathine methyl template being, put around the probe, and whenever these parathane methyl will come and interact with those templates, it will going to get embedded in those, I should say, those templates. And therefore, that will going to change the optical property, one of those optical property like phase or wavelength or intensity. And then you try to measure them for detection of these. And this is exactly what I have tried to show you here. So these are one of those interference pattern. You see, we are talking about 1452 to 1462. That means we are talking about one of those field, one of these interference pattern in this regime. We have considered. So with the change in concentration starting from zero molar, that means it is some sort of a base, or I should say that it is some sort of a calibration point. So you go on changing, increasing the uh, concentration of the go on increasing the concentration, and then you can see that there is a shift in the interference pattern. And this, when you plot this shift in the interference pattern with the concentration, as it is, it linearly increases, and for the higher value of concentration of parathine methyl, it saturates. And it saturates because, when you increase the concentration, the active sites where these water pollutants get binded, they go on getting occupied. That means with time, when the concentration increases, the active sites number reduces, and therefore the shift in interference pattern will reduce, and therefore it saturates. So the whole idea is that if you use different type of other water pollutants like paraxon or parathine or this phenolphthalein, then since the template that has been created is with particular water pollutants, therefore for all other, you see there is some, because some of these will get stick to the surface through some very weak bonding, and therefore you will have very small change in the shift in the interference pattern, unlike what you get with the parathane methyl. You see that it is quite huge. It is almost close to 6 nanometer shift versus some 0.5 nanometer shift. So this makes this system uh, can be utilized for biochemical detection of different type of biochemical detection. And such type of detection has a limit of detection close to around 79.43 femtomolar concentration. This is what I was talking to you about in the morning. I mean, sometime back, that you can have a very, very precise systems with very high limit of detection. Similar type of setup was again utilized for the detection of urea. I have shown you here. So I think here again the limit of detection, or one can go to some picomolar concentration. But the nature of the work remains same. Here, the template that you have to create is corresponds. So this is what some typical biosystems I am talking about. Then let's quickly go to some healthcare applications, or I should say health medicine related applications. So if you see earlier centralized healthcare used to be something like very time consuming and not easily accessible. uh, of course device is one thing, but then these time consuming is something also. If you have a very precise device, then you require it to give you very act fast so that more people can get the benefit. So centralized healthcare was there, and then now you have a wearable systems. Many of us are wearing the smartwatch, which are electronic, but a similar type of watch can also be made using optical. We'll discuss about that. And if you integrate these wearable device to AI, it become much more faster, or I should say, it become much more helpful to the community, and therefore one can recommend the treatment to the people who are in remotely anywhere and everywhere in time. So if we quickly look into the variables, which are optical versus electronics, there are drawbacks. There are drawbacks with electronic variables because these are highly fluctuating. Many times you get a very fluctuating optical signals, and therefore many times you don't believe these infrared thermometer which were utilized during the COVID time. Now people are still going with the mercury-based thermometer or maybe some digital thermometer, unlike the infrared based systems. So because the output of the electronic signal may not be very stable. These are intensity, interrogation, and very specific to a parameter. Then there are stray radiations which may affect them. Uh, since these are electronics based, some materials that are used may be not biocompatible. Long time of these systems are not very great. That means you can use them for a year or so, then you have to discard it, something like that. Unlike optical variables, which have certain advantages, trying to address some of the advantages here, which we'll see. So if we can have, AI, if we can integrate AI to health science or biomedical or medicine, then you have a lot of, you have at the end result will be some enhanced patient care. That means what I'm trying to tell you is that within the quantum you can integrate AI with the healthcare systems, and this is what exactly we're going to see that how AI or a AI assisted wearable device can help. So AI assisted device can be wearable devices, it can be wearable transducers, it can be utilized for any of these parameters. What we'll be talking about mostly is optical. And in optical, if you see, these are the different systems which people use in optical. You use a fiber Bragg rating based systems, you use a microfiber or tapered fiber based systems, use a polymer fiber based systems, or you use a cavity based system. So using any of these systems, one can make a wearable systems using optical. So some of the systems I am trying to show you here is as follows. So this is one such type of a system where PDMS seat is utilized and some sort of an interferometer, which is a hybrid interferometer, is embedded in this PDMS seat. And then you can put this seat, as you can see in this. These are real probes which are placed on your wrist. You can see that these are probes what I'm talking about. So if you start monitoring the bending of your wrist, whether it is a fast bending or slow bending or the direction of a bending, so the advantage of these is that it not only tells you the speed of the bending, but it also tells you the direction of the bending. So these can be utilized for monitoring the a bending of any part of the body, unlike electronics counterpart, which we can only wear on wrist, and that too for some very limited parameters. The optical counterparts can be placed on anywhere of a body, depending upon which parameter you want to monitor. Like for example, bending can be put on elbow, knee, waist, chin, anywhere, any part of the body it can be placed. For physiological monitoring, you can do it. You can wear it for normal breathing. You can do for after running. So all these numbers, if you compare with the systems, what is commercially available electronic based system, these are in line with that. So these are in line with that. So it can be utilized to monitor the physiological. It can be utilized to monitor the physiological parameter of the human. Similarly, if you have to monitor the pulse, you can see that this pulse monitoring can be done using such type of a system, which are also available commercially with the commercial system. But commercial system only pulse can be monitored. With the same system, you can monitor all these other parameters also. Then there are another structure which you can see here. It is some sort of a balloon shape. We are saying it is a balloon waveguide, which we feel has a very strong potential for commercial. And the reasons why we feel so is this is the diagram. These are all commercial systems. PPG is one which you use in your home to monitor the systolic and diastolic peak. And this is our system. So you see, you have only maxima and some sort of a minima here. Systolic and diastolic you have here. This is what you have something like that. But in our, you can see that there are many peaks here, and these many peaks are what are those is something which are already mentioned here that what we are talking about. The idea is that these the developed peaks are based on interferometry, and these are more sensitive than the piezoelectric or PPG based systems which are available in the market. So we have done the calibration and also comparison with all the existing system in the market, and we always realize that uh, you know we can't say that at this point of that time that our system is better than what existing is market, but we can definitely say that our system is giving almost the same results or sometime it is deviation. The deviation is for good or bad, that we don't know, or we don't want to claim at this point of time. But what we want to say is, you see that for different human subjects, these are the readings for heartbeat for with the proposed systems and with the commercial systems. So if I have to just show this is a real time pulse monitoring. You can see the probe is kept here, and these are some pulse which you can say maximum minima. Of course, one has to process this data, and these are raw data which we are showing. These are some wrist bending. You see, every time the wrist will bend, there will be a big peak that will come up. So with every bending in the wrist, a big peak will be there in the screen. So this is again, as I mentioned to you, that this can be utilized for many applications. We have tested for facial motion and wrist bending, for heartbeat, for all physiological monitoring. The beauty is these can be reconfigured and these are scalable. Reconfigured means you tell us that what you want to monitor, we can develop it accordingly. And it can be developed and it can be made available as per the user's requirement. So we are in discussion with some company, and let's see how things go from here. But the whole idea is that these can work. These works very fine, and since these are interferometric based on waveguides, so these has a very long life. You just have to you don't have to worry about it getting deteriorated with time and stuff. So these are also economical, and if produced in bulk, it become further economical. And these are tailorable, as I mentioned, that they can make it as per the user choice. Okay, so we can integrate all these to AI so that you have some optical signal going. It gets some processing of data can be there. Then you use some trained AI model, either it can be KNN or neural network or CNN, whatever you want. And then those trained neural network can tell you about daily health monitoring or early interventions or some unusual stuff that may occur for further result interpretation. What we believe that futuristic AI assisted system can be something like you have your personal laptop, smartphone, or tablet. It goes to cloud, it access the data from there. It goes to the medical, uh, data innovation center, do all type of annotation. And when you have doing all type of annotation, it gets in contact with the health provider, integrate those data with the AI, and then you can give some diagnostic or treatment plan. Only thing is these different laptop and stuff has to be made. These need to talk with the systems that we develop, either it is a smartwatch or contact lens or a smart clothes. So all those interferometry can be integrated with these smart clothes. Okay, so this was all about medical and biochemical and stuff. With aerospace micro crack monitoring, one way to do this, is to create such type of micro air cavity. So what does it mean? Please recall, this is a diagram of a specialty fiber. You have some sort of a air hole here. So, these air holes, if you can make properly or suitably, let's not go into those details how we make it. What I'm trying to tell you is that this air hole, this is also some sort of air hole which can be created. And if you pull this on either direction, either you pull horizontally or you pull vertically, this D will going to change. And therefore, the light which get reflected by this interface or light which get reflected by this interface, this D will change. And as this D will going to change, it will going to change the delta. D is related to this delta and it is related to N. This delta changes, I changes. Therefore, any change in I can be correlated to change in lambda, and this also has N. So change in wavelength per unit wavelength is related to basically refractive index change, and changes this cavity length. So one can monitor a strain by calculating some this delta lambda by some epsilon z. Epsilon z is something is what we say as a microstrain. So this is some process of fabricating a structure which can allow you to change this D. You get a very nice interference pattern. One can make, you go through this process, one can make a very nice interference pattern. It is this structure which has been shown here. So you can just pull it from both the side and one can monitor. So using that, you can see that these are air holes which are inside an optical waveguide using a specialty fibers. Now, what the numbers I am showing you is different minor and major and minor axis, like length of the major and minor. This is like 14 micron by 10 micron. We can make all different type of micron. That means how sensitive you want to monitor, you tell us, we'll able to make. Now, if you place this on any structure, and then if that structure get pulled, we know that from the last slide, we know that this air cavity will going to get pulled. And if air cavity going to get pulled, we can calibrate that in terms of a strain. So any strain that gets created in the structure can be utilized for a strain. We can make multiple such type of a cavity. We say it as a first micro air cavity. This is a second micro air cavity, and this in between is your silica cavity. So basically, these are hybrid cavities, three type of cavity. These are the fabricated probe, what you can see here. And then again, you pull it, all these value will going to change. How these will going to change will look something like this. This is a Fourier transform of those air cavity. You don't have to worry much about at this point of time. You see that air cavity is more dominant. What I'm trying to tell you is as follows. You see these are 4 samples. The size of these air cavity are different. You just, if you see hurriedly, all these numbers are different. For all the 4 cavities, the size are different. Now, since all these sizes are different, we have 4 samples, 1, 2, 3, 4. For all, you see this guy and these guys are changing. These guys are changing. You see these guys are changing. Now you do the analysis of this and then you try to calculate, try to detect micro cracks in any of these structures at multiple locations, maybe 2 or 3 locations at the same time. So these such type of systems can be utilized for determining micro strains in a given structure. Similarly, uh, suppose you have a structure which are, vibrating at 2 different frequencies. Let's say 5 and 10 hertz, 5 and 100 hertz, 5 and 500 hertz. So let's say somebody was asking, can we use this interferometric system for vibration monitoring and stuff? Of course, earthquake monitoring. The earthquake are much smaller in vibration. It's around typically 0.1 or 0.01 hertz. Those are also measurable. One can do those measurements also. So you see that using such type of structure, we can identify the locations. You see this 10 hertz, 5 hertz. You see the type of ramp it is getting. 100 hertz is getting different than the 5. One can do the analysis and very precisely you see you are able to monitor 5 hertz, 10 hertz, 15 hertz, 100 hertz, 500 hertz on the same plot. You see the type of noise it is having. The signal is so clean with respect to some of these noise here. What I'm trying to tell you is that you can identify the vibrations of a structures at multiple locations using such type of model interferometer. Some mobility aspect I was supposed to, some high precision mobility. So we say it as a smart traffic monitoring. So what we do in a smart traffic monitoring is as follows. So we put 2 type of these smart sensors here. You can see them on the road here. These are yellow patches here. These are some couplers. Forget about these are some experimental setup. These are all the sensors fabrication. You don't have to worry much on these aspects. What is more interesting is this. So this is your some SLED or source spectrum. This is your probe spectrum. We just study these part of the spectrum when the vehicle moves. So these part of the spectrum you see, it give you some with some 4 second over 4 second. It is some noisy type of signal you get. We do some analysis of this signal where these sensors can be put on the road. Optimized depth is from the, if you see this any of these road, you have to put it around 1.2 centimeter deep. You have to embed them on the road. So these are embedded sensors on the road. And it gives you a sensitivity, load sensitivity of 40 picometer every 100 kg. That means if 100 kg person stand on those sensors, the interference pattern will going to shift by 40 picometer. So we are not talking about person, we are talking about big and heavy vehicles. And this is what we're going to show you. This is a bicycle which went through those systems. This is a car. You see all these are signals which we are real-time signal. What we have monitored, these are 36 picometer, these are 125 picometer with car, 47 picometer with motorbike, and around 675 picometer with bus. So using these systems, we can monitor different type of vehicles. Also, it is important that we do not only monitor what type of vehicle, we do not only monitor the load, which is the weight, but also depending upon the axial distance, which are, you can see that these peaks are either getting closer or farther apart. You see, the separation between them is smaller, bigger, much bigger, much bigger. So these also tells you the axial distance through which we can monitor the nature of the vehicle also. These are some analysis which can be done, uh, assuming our systems, what type of load it can do. We do some speed estimation through this, so it can also be utilized if some vehicle is over speeding or not. So this is some, speed was 30 kilometer for the bike, 7.3 kilometer for. So how we do this? These are some calculation. You don't have to worry much about this. Important thing is these are some numbers which you can see. These are the axle distance numbers which are required in different case. One can do that, and the axle can also be counted whether it is a four-wheeler, two-wheeler, 18-wheelers and stuff. This is the last part of a talk. I am slightly hurrying so that to be within the time. And this is somebody was asking about NV centers and stuff. So magnetometer using NV centers can be done. So what you take is you take some diamond probe here, and then you have some magnetic sample. Depending upon this distance, you try to map these magnetic samples. These are typical experimental setup that I required to study these NV centers here. These are slightly complex systems. So you've got some sort of a stage, you have a sample, you have some microwave antenna, you have some mirrors, which are very typical for this. You come with a laser, it falls on the simple part of these will go to this fiber coupled photo detector, which will go to, for collecting the fluorescence signal. The signal which we are interested here is here. You can also use the microwave source because it is this microwave source which will help you to tune the magnetic field or to monitor the magnetic field using these NV centers. This is again one diagram showing you how this can be utilized using. I mean, these two diagrams are in same, but they're relatively simpler. The same magnetic field sensors we also develop in our lab can also be utilized for bioimaging. So you can use some sort of a DNA using such type of NV centers attached. Some site of DNA attached to NV centers, you can do them using NV centers based magnetometry for very high precision or very small value of analyte which you want to detect. So I think I just hurriedly I was trying to go through some water pollutants, then healthcare for respiration, heartbeat, which can be utilized for elder care facilities, physiological monitoring. One can use those wearable systems into a smart clothing. Then I try to show you some strain measurement which can be utilized for health monitoring, and then some smart traffic for mobility, and then can some NV centers be integrated with can be integrated along with microwave source for magnetometry applications, and also if properly coated with some biomolecules, it can be utilized for DNA detection and stuff. So with this, thank you very much for your kind attention. And sorry for hurriedly going through the second part of the talk.
Thank you, sir.
Thank you.
There
So
are
I
a
would
couple
love
of
to take
queries.
yes.
They have in chat box. This is like, is there any bandwidth constraint for the mass sender interferometer?
So I have already replied to that question. For Mach-Zehnder interferometer, the bandwidth get limited by the type of the source that you use. So in general, for any sensors, the bandwidth will get limited by the source and the detector that what you're using. In general.
can you suggest a simulation software for quantum sensing application?
I have told it is FEM and FDTD based systems. I think you are muted.
Hello.
Ha.
So there was one question like how these types of optical variable devices are manufactured, is fabricated.
How these type of optical wave devices are manufactured? We do develop some of these devices in our lab, where you have to make first you have to make a system which can be flexible. We basically use some type of organic polymer, and after doing some computational study, we try to understand that how thick it should be, what should be the material used, and then we try to embed our interferometer into that. Once we have embedded the interferometer into that, then we characterize them. Once we have characterized, then you use it for on human application. So these can be done. What is the advantage of using traffic monitoring sensor over regular cameras or radar? So I mean, these are very standard questions. You see, using regular cameras or radar can also be utilized. So when you go to a market to buy a paracetamol, you get Dolo 60, 650, you get Crocin 650. So all these are medicine, but that depends. Certain medicine will be useful for some person, certain medicine will be useful for other person. When you are talking about traffic monitoring particularly, please note that these cameras, if your weather is bad, your camera will not going to work. Same goes for radar. Radar cannot give you a resolution what the proposed systems can give. So all systems have certain limitations. And for example, if you ask the limitation of our systems, the limitation of our systems is that we have to make our systems on the road. There has to be a corridor through which the vehicle has to move. Then only our systems will work. So every system has a limitations. As I mentioned, that camera will have limitations in terms of bad weather. It cannot work. Our systems can work in very bad weather because these are interferometric based systems. These are very rugged in nature. Radars, I have mentioned, the resolution is the issue. So I think with every system there are some if and but. One can always integrate the two systems to get the best out of it. Sir, is anti-collision sensor available? I have not much idea. If you are talking about something like Kavach and stuff, I don't have much idea. Anti-collision, if at all there is a sensor, but if two body are coming closer, that depends at what speed you are talking about. But any two body coming closer, one can make a sensor that if there is a touch of one body, you can say something like touch sensor. But touch sensor is not collision sensor. Anti-collision sensor, if I believe you are talking something related to train and stuff. So till now, I have not seen any such, but I believe there will be something similar in line with the Kavach. Can we use a squid sensor instead of magnetometer? Yes, people are using a squid sensor, but it is expected that NV center in future will going to get replace the squid in future with the NV center based system. It is expected. Professor Saab, you are muted.
Hello.
Yes.
Yes, sir. So thank you very much for your time and your lecture.
Thank you. Thank you.
You have already responded all the queries to the participant. So we are closing the today's session, and once again thank you speaker and the participant for joining the meeting. We will
Thank you.
meet tomorrow as per the schedule.
Thank you.
sir.
Thank you very much for giving me the opportunity, and thanks every listener. So please feel free to get in touch with me over my email rj@iitbbs.ac.in. Thank you so much.
Thank you. Yes, sir.